Okay, let's continue our discussion of conservation of matter. We're going to move forward and start discussing chemical equations now. So as a foundational concept, we need to understand that matter cannot be created or destroyed by any physical or chemical change. So physical changes, the laptop that you saw there, getting smashed by a sledgehammer, it changes its form, right? There's a physical change, but the atoms that were present there, they changed location, but they're not being created or destroyed in the process. Chemically, there we had our campfire, right? So a lot of the times you think that, fire, it burns, it destroys, but that's not really true. All that happens is the wood, the chemical energy that was stored in the wood, that gets used, but the matter itself is just changing into a different form. It's being expelled as gases. So we're going to be exploring that in a little bit more depth now. So we call this the law of conservation of matter. And again, matter cannot be created or destroyed by any physical or chemical change. Chemical equations allow us to see what kinds of chemicals or what substances will appear at the beginning and at the end of a reaction. They also tell us how many of these things there are. So a couple things to bear in mind with this. First, we need to understand the symbols that are used in these equations. The plus, just like in a math equation, it's addition. Things are being combined, they're coming together. The arrow that you see, this indicates that we have a change, and you can think of it just like an equals sign. In parentheses, these lowercase letters you see identify that this is S, a solid state, L is liquid, G is gaseous, and AQ tells us that we have a substance that has been dissolved in water. So what we're going to do is we're going to take a look at just a simple chemical equation. I'm going to start with one atom. Let's say this atom is a copper atom. So a copper atom would be Cu, and that's solid. Now what I'm going to do is I'm going to combine my copper with a chlorine gas. So this chlorine, a chlorine gas molecule, consists of two chlorine atoms that are covalently bound together. So that is going to look like Cl with a subscript of 2. We write G to indicate it's a gas. So what we have here at the beginning of our reaction, our copper and our chlorine gas, these are what we refer to as the reactants. Okay? The things that are going to react are called reactants. Now, to show that they're going to come together, we're going to draw our plus sign. Okay? So this indicates the copper atom joins with the two chlorine atoms, and then you draw the arrow to indicate they're going to chemically change here. They're going to change into this new compound. Okay? So this is going to be bound together, a single copper with two chlorines, and we write that symbol as CuCl2, and it is in a solid state. So copper and chlorine make our copper 2 chloride is its technical name, but you won't be responsible for knowing that just yet. Now, before we said that the things that are going to react are known as the reactants. The things that are formed, these chemicals, are called products. So the reactants are going to come together, the products have been made, they have been produced. Okay, so the before, reactants, the end, the products. Now, balancing these equations is necessary. If you consider the law of conservation of matter, it says whatever you have in the beginning, you're still going to have in the end. So our process is we're going to add coefficients, so we end up with the same number. We'll have the same number of each atom. That happens before the reaction. It's still going to be present after. So we're going to start this time with these two reactants. I've got Fe, so this is solid iron, and Cl2 gas. So Fe solid plus Cl2 gas. Now these are going to come together and they form iron 3 chloride, FeCl3. So we draw on our arrow to show this is the beginning, the reactants. These are now our products, the FeCl3 solid. Now, the thing to consider is we have to make sure we have the same number of atoms on both sides. So the first step in the process is to count. We're going to count up. We see that we have iron and only one atom of iron here on the left. Then chlorine, count them up, we have 2 chlorines on the left. I like to go ahead and draw on a vertical line just to help me separate the counting on the left from the counting on the right, because we're going to compare the left, the reactant side, to the right, our product side. Now in FeCl3, I'm going to write symbols for both iron and chlorine below that, just to keep straight my count for this specific compound. So the Fe is 1, and the Cl, you see a subscript of 3, so there are 3. Now notice, they're not balanced, so what we're going to do is we're going to start adding coefficients. You can see that the problem that I face right now isn't iron. Iron, I have 1 iron to 1 iron, that's fine. Visually, you know, the 1 blue and the 1 blue, that's good. But you see that I have 2 chlorines, but I have 3 on the right. So I need to get more chlorines to the left side. So if I add a coefficient of 2, what that does for me is it allows me to multiply this number by the coefficient. So 2 Cl2s, 2 times 2 gives me now 4 chlorines. Well, now the problem is I don't have enough chlorines on the right side. So what I'm going to do is now add a coefficient on the side that has too few. I'm going to add a 2 here, and notice now I have 2 times 1 iron makes 2 irons. 2 times 3 chlorines makes 6 chlorines. Well, if I go back now, I'm not going to be able to work with this coefficient of 2. But in order for us to make 6 chlorines, I can take 3 Cl2s would make 6 chlorine atoms. And now I've got 6 and 6. Chlorine is good. Check back now though, I have 2 irons on the right now, so I have to do a coefficient of 2. And now I have a balance. Left side, 2 irons. Left side, 6 chlorine atoms. Right side, 2 iron atoms. And right side, 6 chlorine atoms. So visually, you can see now 2 blues on the left, 2 blues on the right. 6 yellows on the left, and 6 yellows on the right. Now, go ahead and take a second and work out these practice problems. I'll assume that you've taken that time, and now I will begin. Let's state the law of conservation of matter. The law of conservation of matter states that matter is neither created nor destroyed in any chemical or physical change. Okay, so you need to really internalize that. You've got to know that law. The law of conservation of matter. Matter is neither created nor destroyed in any chemical or physical process or change. Now, let's balance these equations. So, Na solid, I've got 1, Cl2, 2, Na1, Cl1, 2 Cls to 1 Cl. Add a coefficient. Now I have 2 Cls and 2 Cls. I have 2 NAs though, and I'm going to have to add, now we have 2 NAs. Mg and O2 make MgO. Well, I have too few oxygens, so I have to add coefficient of 2. That throws off the magnesium, so then I can put in 2 magnesiums, and that one balances now too. So now what we're going to do is we are going to look here at my potassium, H2O. They come together to make H2 and KOH. So we're going to start. We have 1 potassium. Now this is a little more complicated. I'm going to work it with the numbers below. So there's my line. K is 1, H is 2, O is 1, H is 2, K is 1, O is 1, and H is 1. One thing that we have to notice here, though, is that on the right side, I have the same atom that appears in 2 different substances. So what I like to do on these is notice, since I have both of these, I'm going to say that the H total I'll keep track of over on the side. The H total is 2 and 1. That's 3. So what we're going to do is we're going to see, well, where do I have too few? I have too few hydrogens. So what we can do is we can say, well, I only have 2 hydrogens on the left, I have 3 on the right, so we'll add a coefficient on the left. This 2 makes this now 4 hydrogens, and the 2 times the 1 oxygen makes that a 2. Over here, now I can see that I have too few hydrogens on the right, and I have too few oxygens. So now let me try to fix the oxygen. If I have 2 oxygens on the left, to get 2 on the right, I add a coefficient of 2 here. This changes all of these to 2 atoms, and I have to update my total of hydrogen. 2 hydrogens here with 2 hydrogens here makes a total of 4 hydrogens. Oh, now the hydrogen is good, the oxygen is good, but I now have too few potassiums on the left. If we add a coefficient of 2, now we have 2 and everything is balanced. Now our final combination, this final reaction to balance, we have carbon, and hydrogen. There's 1 and 4. The oxygen is 2. We've got our carbon dioxide, so that's C and O, 1 and 2. And water, H and O, 2 and 1. Notice we have oxygens in both of these, so the oxygen total I'm going to keep track of on the side. Now, as I compare these, I'm going to notice first off that I have 4 hydrogens here. I have 2 hydrogens here. I have 2 oxygens here, and I have 3 oxygens here. So I'm going to begin by fixing the hydrogen problem. If I do a coefficient of 2, I now have 4 hydrogens, which is what I want. But that also changes this to have 2 oxygens from the H2O, and a total of 2 and now 4 oxygens total. On the left side, you notice I have 1 carbon, and I have 1 carbon on the right. Pretend that arrow was there. And then my O2, only 2 O2s here, a total of 4 O2s on the right, but a coefficient of 2 fixes that problem, and now everything is balanced.